Hi everyone, so here's a quick video to go over our probability rules, this time with Venn diagrams. So I've constructed an example. Suppose we have a survey that finds 75% of breakfast customers put butter on their pancakes, 80% put maple syrup on their pancakes, and 65% use both. So I've constructed our Venn diagram. We have event A, those who put butter on their pancakes, event B, those who put maple syrup on their pancakes, and then their intersection, those who put both butter and maple syrup on their pancakes. And then the probabilities I've written in here reflect the data that I've given in the example. So the probability of event A, that's 0.1 plus 0.65 for a total of 0.75. That is those who use only butter plus those who use butter and maple syrup for a total of 75% of those surveyed. We can calculate the complementary probability using our complements rule. So 1 minus 0.75 has to give us those who don't use butter on their pancakes. And so another way to calculate that would be those who use only maple syrup or those who use neither. Probability of event B is probability of selecting somebody who uses maple syrup on their pancake. And so this is going to be those who use only maple syrup, 0.15, plus those who use maple syrup and butter, 0.65, for a total of 0.8. That's the 80% of those who use maple syrup on their pancakes. And again, we can use our complements rule to find the percentage of those who don't use maple syrup, and that's 20%. And again, in order to calculate that 20%, we alternatively could have added up those who use only butter and those who use neither. Okay, so we can apply our addition rule though, and we can find the probability of the union. So the probability of the union is the probability of event A plus probability of event B minus the intersection. And so what this is doing is, suppose we want to find those who use either butter or maple syrup, the probability of a randomly selected breakfast customer using either butter or maple syrup on their pancakes. In order to do this, we'll add up the probability of selecting somebody who uses butter plus the probability of selecting someone who uses maple syrup and subtract off the probability of selecting somebody who uses both. And the reason why we want to do that is because, well, probability of event A includes the intersection and probability of event B includes the intersection, which we have now included twice, so we need to subtract off. So we find the probability of selecting somebody who uses either butter or maple syrup on their pancakes is 0.9. 90% of customers use butter or maple syrup on their pancakes. Okay, so suppose we want to consider a situation where we have mutually exclusive events, where we have an empty intersection, we have disjoint sets. In order to make this happen, what I did is I left the probabilities of those who use only butter and the percentages of those who use only maple syrup the same. And what I did is I took the percentage in the intersection, probability of the intersection, and I swamped that into the neither category. So here's the probability of event A is 0.1, so 10% of people use only butter. Probability of event B is 0.15, 15% of people use only maple syrup. And then the complementary probability includes the other set plus those who use neither. Okay, so if events A and B are mutually exclusive, we know their intersection is empty, the sets are disjoint, so the probability of A and B together is 0. So the example, just to write it out, would be, suppose a survey finds 10% of breakfast customers put butter on their pancakes, 15% put maple syrup on their pancakes, 0% use both. Now let's go ahead and find the probability of the union. Well, the probability of the union is going to be probability of selecting somebody who uses butter or somebody who uses maple, and clearly it's just going to be the sum of those two probabilities. So the probability of the union of A and B is just the probability of A plus the probability of B minus their intersection, which is trivial, it's 0. And so we find the probability of selecting somebody who uses butter or maple syrup is 0.25. 25% of consumers use butter or maple syrup on their pancakes. Okay, so now let's return to the original example, but this time I'm going to be exploring conditional probability. So the numbers here are the ones that I introduced originally at the beginning of the video. Same numbers here in the right-hand column. And what we're interested in now is answering the question, given that we might have selected somebody who uses maple syrup, what's the likelihood that they also use butter? Right? So what information do we learn about somebody's butter using habits by virtue of knowing that they use maple syrup? So here's the statement, mathematical statement. Probability of event A conditional at event B is equal to the probability of the intersection divided by the probability of event B. So we have the probability that a customer uses butter conditional on being somebody who uses maple syrup. So it's 0.65 divided by 0.8 or 0.8125. What's going on here? Well, what we're essentially doing is we're looking to find the ratio of the intersection to the entire circle B. So this is giving us what proportion of maple users are butter users. Suppose we want to ask the other question. Suppose we have selected somebody who uses butter. What's now the probability that they use maple syrup? What information do we learn about somebody's maple syrup using habits by virtue of realizing that they use butter? So this is mathematically the probability of event B conditional on A. It's equal to the probability of the intersection divided by probability of event A. So here we have essentially the ratio of the intersection to the probability of the entire circle A, right? And so we have the conditional probability of using maple syrup, given that you're using butter, is 0.867. So what this is telling us is it's saying, given we have selected someone who uses butter, what's the likelihood they also use maple syrup? Or what proportion of butter users are maple users? Okay, so now what I'll show you is the same sort of analysis, but suppose instead we have independent events. So two events are independent when the probability of their intersection equals the product of their respective probabilities. So the probability of the intersection, A and B, equals the product of the probability of event A times the probability of event B. And you'll see that that's true here. Now clearly I've had to rearrange, or I had to select new numbers to make this happen. So the probability of event A is 0.8, probability of event B is 0.75. Probability of the complement of event A is 0.2, and probability of the complement of event B is 0.25. You can check and add those up for yourselves. Now we'll look and see, are these events independent? Is the probability of the intersection equal to the product of the probabilities? Well, sure. The product of the individual probabilities is 0.8 from probability of event A times 0.75 from the probability of event B, and that's 0.6. But look, that's the same as the probability of the intersection. So indeed, we do have independent events. Now I'll explain what this is really telling us when I go through the example. So mathematically, what we have, if we have independent events, is the probability of event A given event B has occurred is just the probability of event A. No additional information about the likelihood of event A has been gained by virtue of observing B. So this would say the probability that a customer uses butter, conditional on being a maple syrup user, is the same as the probability that a customer uses butter. Right, so let's do this with numbers. Probability of event A conditional on B is 0.6 divided by 0.75. That's just 0.8. That's the probability of event A. What this is saying is, given we've selected someone who uses maple syrup, what's the likelihood they use butter? Well, this is still actually the ratio of the intersection to the whole circle B. However, this ratio matches the probability of A. So what's going on here? It's saying 80% of maple syrup users are butter users. And since the proportion of butter users among maple syrup users does not differ from the general population of those who use a topping on their breakfast, we don't gain any additional insight into the likelihood of having selected a butter user by virtue of having selected a maple syrup user. So that's what it means for the events to be independent. I'll look and take a look at the other side of things. So suppose now we are selecting a customer we want to know, conditional on having selected a customer who uses butter, what's the probability that customer uses maple syrup? Well, since the events are independent, we know the probability a customer uses maple syrup, conditional on using butter, is just the probability the customer uses maple syrup. So here we have the probability of event B given A is just 0.6 divided by 0.8, which is 0.75, or that's just the probability of event B. So symmetrically, given that we've selected someone who uses butter, what's the likelihood they use maple syrup? This is still the ratio of the intersection, this time to the whole circle A. However, here this ratio matches the probability of event B. So we see 75% of butter users are also maple syrup users. And since the proportion of maple syrup users among butter users does not differ from the general population of those using a topping on their breakfast, we haven't gained any additional insight into the likelihood of having selected a maple syrup user by virtue of having selected a butter user. Okay, so more generally, mutually exclusive events are those that cannot both happen at once. So an example would be either the Cleveland Cavaliers win the NBA final or they lose the NBA final. Independent events are those that have no bearing on each other, but may or may not happen simultaneously or at the same time. So an example would be, suppose the Cavaliers win the NBA Finals. Well, at the same time, Pittsburgh Penguins may or may not win the Stanley Cup. And knowing the outcome of one contest tells us nothing about the outcome of another contest. They can both happen, or neither could happen, or one or the other could happen. So here's another example. For mutually exclusive, the occurrence, for instance, of heads and tails as a result of a coin toss are mutually exclusive, right? So it's one or the other is going to happen. Another example for independent events, the outcome of any coin toss and the roll of any die are independent. So knowing that I might have rolled a 5, if I roll a die, tells you nothing about whether or not I should also toss a head or a tail, right? So those events are going to be independent. Okay, so that's all for now, and I will go ahead and upload this full transcript as well right next to the video. So in case you didn't see this when you noticed the video, this example document will be there as well. All right, I'll see you next week.